Hello everyone. Welcome to today's video lecture. My name is Dr.E.Purushotham, Professor of Physics, Department of Basic Sciences, School of Sciences and Humanities. Today, I am going to discuss about Newton's laws of motion and their applications. So, what are the importance of Newton's laws of motion? So, why we need to learn Newton's laws of motion? So coming to first one, this is first one, innovation in technology. So we try to understand here how Newton laws of motion are not limited to physics, classrooms, or mechanical systems, but also play a significant role in the field of computer science and engineering and all the other disciplines also. So let us go through each of these areas in details. First one, coming to innovation technology. Newton laws inspired us to think systematically about cause and effect, just as forces produce predictable changes in motion. So in technology, structured problem solving leads to innovation. By understanding these physical principles, engineers and scientists develop creative solutions, whether it's designing safer cars, faster processors, or energy efficient systems. So, Newton laws approach to laws of motion teaches us how to build technologies based on solid fundamentals. Coming to next one, you see here algorithm development in especially in computer science, algorithm often need to simulate or analyze motion. Think of self-driving cars, drones, even gesture recognition. Newton laws provide the mathematical foundation for motion detection and navigation, that navigation related algorithm. For instance, predicting the path of a moving object or determining collision avoidance. In robotics, relies on applying force, mass, and acceleration relationship, that is equal to force is equal to ma, derived directly from Newton's second law. Coming to this VR and AR. VR, virtual reality, AR, augmented reality. So in this VR and AR, user experience depends on making virtual environment feel realistic. Newton laws are applied to model objects, interactions like how a ball bounces back, how gravity pulls objects down, or how collisions feel. These laws ensure immersive experience, immersive experiences, where movement in the virtual world mimic those in the physical world, enhancing both entertainment and training applications. Coming to robotics, coming to robotics. Robotics is another domain where Newton laws are crucial. Every robotic movement, whether it's lifting, gripping, or navigation, depends on precise calculation of force, torque, and acceleration. For example, robotic arms in manufacturing need to apply just the right amount of force to pick delicate objects without breaking them. Similarly, autonomous robots calculate forces for movement on different terminology and different related applications. These under fundamental principles. So coming to this simulation and game development. So one of the most visible applications is in gaming and simulation. When you play a racing game and the car responsible realism to accelerate, braking, or collision, that is environment engaging and believable. Without Newton's principles, games would feel artificial and unrealistic. So, what I am saying, Newton laws of motion continue to influence not only physics and engineering but also cutting edge areas of computer science and all other disciplines. They connect the physical world with the digital one, helping us innovate, simulate, and create technologies that are both useful and immersive. So, coming to Newton laws of motion and their applications. So, Newton's first law or Newton's laws of motion in 1686. You try to understand. In 1686, Sir Isaac Newton introduced his three laws of motion, which established the relation between force and motion. These laws are known as Newton laws of motion. What I am saying, in 1686, Sir Isaac Newton introduced his three laws of motion, which established the relation between force and mass. These laws are called Newton laws of motion. Newton laws of motion. So that is Newton's first law, second law, and third law. These are the three Newton laws. So coming to Newton's first law, what is Newton's first law? Every object continuous in its rest, every object continuous in its state of rest or of uniform velocity in a straight line as long as there is no external force or there is no net force acts on it. What I am saying here, in 1686, Sir Isaac Newton introduced his three laws of motion, which establishes the relation between force and the motion. These laws are known as Newton's laws of motion. So, in this Newton's laws of motion, coming to first law, Newton's first law of motion, every object continues in its in state of rest or of uniform velocity in a straight line as long as no net force acts on it. What I am saying, try to understand, an object will remain at rest in uniform motion unless acted upon by an external force. That is called Newton's first law. Or you can see here, every object continues in its rest, state of rest, or of uniform velocity in a straight line as long as no net force acts on it. No net force acts on it. It gives a concept of force and inertia. The Newton's first law gives a concept of force and inertia. It is also known as law of inertia. The Newton's first law is also known as law of inertia. The measure of the inertia on object gives the mass. If mass is more, the inertia is also more. If mass is less, the inertia is also less. Inertia is also less. The measure of inertia of an object is mass. So, what are the real life examples? You try to understand. The carpet is beaten with a stick to remove the dust particle due to the inertia, due to the Newton's first law. A person sitting on the a person sitting or standing on a bus fall back when the bus suddenly starts moving forward. A person sitting or standing on a bus fall back, the bus suddenly starts moving forward. Another one, a book on a table, a car keeping moving, a car keeps moving unless brakes are applied to slow it down. A dropped pencil falls straight to the ground due to gravity without any force acting on it change its path. The passenger in a stationary train, the passenger in a stationary train falls back when the train starts suddenly. This is the real life examples. These are the real life examples of Newton's first law. So you are observing the train is moving. One person is jumping out from the train. So his velocity and train velocity at starting he is moving. So due to the inertia, due to the mass of the person, we can observe he fell down. So coming to second example, if there is no external force acting on the body, the body is moving with a uniform motion unless acted upon by an external force. That second example also we need to understand. The first and second example. The first example is also Newton's law of motion, Newton's first law of motion due to the inertia. Second one is also Newton's first law of motion. So an object, if at rest, it is at rest. In uniform motion, unless acted upon by an external force, it can move with the uniform motion. So try to understand here Newton's first law. You see here Newton's first law of motion, that is inertia. An object will not change its motion unless acted on by an unbalanced force. We know very well. If it is at rest, it will stay at rest. If it is in motion, it will remain at the same velocity or with uniform velocity. For example, you can see here two objects. First object mass m is equal to 30 kg. This is second object. This is the first object m1 30 kgs. For example, this is second object m2 is equal to 300 kgs. Objects with a greater mass have more inertia. For example, this 30 kgs, the mass is less, m1 is less. So the inertia also less. Here the mass is more, the inertia is also more. So we will give the conclusion. Objects with a greater mass have more inertia. It takes more force to change their motion, to change their. So coming to next example, Newton's first law and also inertia. The variation on the classic pull out the tablecloth trick is a greater example of Newton's first law. Nothing pushes or pulls the tennis balls sideways. So inertia mandates that they do not move horizontally. So we can observe clearly the tennis balls, how they are moving, depending on their inertia, according to Newton's first law. This variation on the classic pull out the tablecloth, just to pull out the tablecloth, trick is a great example of this trick, Newton's first law. Nothing pushes or pulls the tennis balls sideways, so inertia mandates that they do not move horizontally. So coming to next example, you try to understand. So this ball is at rest. According to Newton's first law, an object will remain at rest. It is at rest. If he is applying some force, the ball moves when the force is applied. The force is applied on the ball due to hitting here, so the ball can move. So applications of Newton's first law, you can see an athlete continues to run for some time even after reaching the finishing line. This because they cannot stop suddenly due to the inertia, due to the Newton's first law. The Newton first law is also known as law of inertia. A switched off fan or a switched on fan. The switched on fan slowly increasing the rotating. Switched off fan will continue to move for some time till friction stops it. So Newton first law is an application of using the first law is an car safety equipment. The car safety equipment like seat belt and airbags. The Newton's first law is used in the car safety equipment, that is seat belt and airbags. When there is a crash or sudden braking of the car, the passengers are pushed forward. The top part of their bodies is still at the same velocity as that of the car before the crash and continue to move forward due to the inertia. The seat belt prevents them from langing forward. An airbag inflates quickly in case of a crash and prevents the driver or passenger in the next seat from hitting the dashboard. So, coming to next, you try to understand the athletes are running. You try to understand, try to see here. An athlete continues to run for some time, even after reaching the cross line or finishing line. This is because they cannot stop suddenly due to the inertia. This is the best real life example of law of Newton law, that is Newton's first law, and also law of inertia. An athlete continues to run for some time even after reaching the finishing line. This is because they cannot stop suddenly due to the inertia. So Newton's law, that is first law, you can observe here. This is the switched on fan. Switched on fan. This is a switched off fan. A fan that is just switched on will gradually increase its speed until reaches a steady rotation, overcoming frictional resistance. So switched on second fan, coming to second fan, a switched off fan will continue to move for some time till friction stops it due to the inertia. Due to inertia. The switched off fan and switched on fan. So the switched on fan will gradually increase its speed until it reaches a steady rotation, overcoming frictional resistance. And switched off fan will continue to move for some time till friction stops it due to the inertia. So application of Newton's first law in car safety equipment, that is seat belt and airbag. When there is a crash or sudden braking of a car, the passenger are pushed forward. The top part of their bodies is still at the same velocity as that of the car before the crash and continues to move forward due to inertia. The seat belt prevents them from leaning forward. An airbag inflates quickly in case of a crash and prevents the driver or passenger in the next seat from hitting the dashboard. So, Newton's second law. This is the Newton's second law. What is Newton's second law? We can see here the rate of change of d by dt is the rate of change of momentum p. The momentum p is equal to mass into velocity. The rate of change of momentum of a body is directly proportional to net force acting on the body. The net force acting on the body. That is the Newton's first law. So the rate of change of momentum of a body is directly proportional to the net force or external force acting on the body or acting on it, where momentum p is equal to mass into velocity. So the net force on object is equal to the product of object, mass and acceleration. So mass and acceleration, the product of mass and also acceleration. The net force or external force is equal to the product of mass and the acceleration of the object. So try to understand here. So we need to give here mathematical expression for Newton's second law. You see here the acceleration denoted by A. The acceleration is directly proportional to the net force acting on the body, F net, the net force acting on the body, and also inversely proportional to mass of the object. Inversely proportional to mass of the object. So we can write here the acceleration is directly proportional to net force acting on the body by mass of the object. So we can write this is net force is directly proportional to mass into acceleration. So here you try to see F bar net force is equal to some proportionality constant K into MA bar, where K is the proportionality constant. Proportionality constant. If K is equal to 1, if K is equal to 1, the net force acting on the body is equal to MA. So this is the net force. You see here the net force on object. The net force on an object is equal to the product of object's mass and acceleration. Or we can also take here summation of force is equal to mass into acceleration. This is the mathematical formula. F is equal to ma, or F net force is equal to m into a. This is the mathematical expression for Newton's second law. Mathematical expression for Newton's second law. So coming to real life applications, you see here example. So first example, real life example, pushing a cart. It is easier to push an empty shopping cart than a cart filled with heavy grocery or heavy groceries, because the filled cart has more mass and need more force to accelerate. For example, empty. So we can see it is easier to push an empty shopping cart than a cart filled with heavy groceries, because the filled cart has more mass and need more force to accelerate. Coming to second one, second example, tug of war. In a tug of war game, if one team pulls pulls harder than other, they are more likely to accelerate the opposing team in their direction due to the difference in force applied. Another one, pushing a light ball is easier than pushing a heavy ball. Coming to C. So this is the empty cart. This is the filled cart. This empty cart mass is less. So we need to apply the force is also less. So it is easily moved from one place to another place. So it is easy to move from one place to another place. In this filled cart, the mass is more. Mass is more. So we need to apply more force on the cart. It is easier to push an empty shopping cart than a cart filled with heavy groceries, because the filled cart has more mass and need more force to accelerate. So coming to tug of war. So you see here balanced and unbalanced force here. This is the tug of war. In a tug of war game, if one team pulls harder than other, they are more likely to accelerate the opposing team in their direction due to the difference in force applied. We can observe here clearly. So, applications of Newton's second law of motion. A ball kicked with stronger force moves further distance due to higher acceleration. Pushing a heavy object requires more force to be applied due to the higher mass. An application of using the second law is in designing fighter jets. Fighter jets need to quickly turn around to dodge artillery fire from the ground or enemy planes. Jets with lighter mass are easily to turn around quickly with lesser force. Like this heavy aeroplane, like more time to change direction due to their inertia. So you try to see here the Newton's second law is used in designing the fighter jets. You try to understand here, you see here, an application of using the second law is in designing fighter jets. Fighter jets need to quickly turn around to dodge artillery fire from the ground or enemy planes. Jets with lighter mass The jets are having very light mass, so they can easily turn around quickly with lesser force. For example, the aeroplanes are having more mass, it has more inertia. So heavy aeroplanes takes more time to change direction due to inertia, due to the inertia. So coming to try to understand the Newton's second law, if we are applying the force on the body in this direction, it accelerate with acceleration A. So m is the mass of the car. So we can apply Newton's second law, F is equal to ma. F is equal to ma. So second example, we can observe the batsman hitting the ball with a bat. So he is applying some force. He is applying some force on the ball. The ball mass is m. Hitting with some force F, the ball move away. This is another example. So coming to Newton's third law of motion. For every action, there is an equal and opposite reaction. So that is the Newton's third law. For every action, there is equal and opposite reaction is the Newton's third law. When two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. So we try to understand this is force F12 is equal and opposite to F21. Let F12 be when two bodies, this is one body, this is another body. So on first body, the force acting 1, 2, that is action force. On second body, the force F21, that is reaction force. When two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. So we can write here F12 is equal and opposite minus F21. Let F12 be a force acting on a body 1 due to body 2 and F21 be a force acting on the body 2 due to body 1. Then F12 is equal to minus F21. It is clear that from this equation, F12 is equal to minus F21. The two forces are equal in magnitude but opposite in direction. One of the two forces involved in the interaction between two bodies may be called action force. The other force will be called the reaction force. What I am saying here, it is clear that from this equation F12 is equal to minus F21, the two forces are equal in magnitude but opposite in direction. One of the two forces involved in the interaction between two bodies may be called action force. F12 is called action force, and the other force F21 will be called the reaction force. Reaction force. So coming to real world applications, gun gives a jerk, boatsman pushes a river bank, pushing a wall, sitting on the chair, walking. To try to understand. So gun gives a jerk to shoulder of the gunman. If he is firing, the gun will give some jerk on the shoulder of the gunman. On firing a bullet from it. Second example, boatman pushes the river bank with a bamboo pole to take his boat into the river. So pushing wall, you can see here, when you push a wall, the wall pushes your hand back and also legs back. Rocket motion also, we can take the example. A rocket goes up because it shoots burning gases downward. These gases push the rocket upward with the same strength, means the same force, lifting it into the sky. Sitting on the chair. When you sit on a chair, your body weight pushes down on the chair and the chair pushes up on you with an equal force. Walking also, try to see here, walking. When you walk, your foot pushes the ground backward and the ground exerts an equal and opposite force. It helps to move forward. So coming to this one, Newton's third law, what he is doing? So he is pushing a wall or pushing a pillar. He is pushing a pillar. When you push a wall or pillar, the wall pushes your hand back and also legs back. You try to see and try to understand clearly. He is trying to pushing that pillar. When the person push a wall or pillar, the wall pushes back on his hands and also legs. What I am saying simply, when you push a wall or pillar, the wall or pillar pushes your hand back and also legs back. Coming to next one. A gun recoils. You try to understand. Here, gun recoil. You see here. A gun recoil while firing. While firing, it means that the gun is pushing back when bullet is fired at high speed. Coming to next one, this is rocket. Coming to rocket example. Rockets are excellent examples of the application of the third law, Newton's third law. The thrust of high pressure gases by burning fuel from the engines pushes the rocket up with a very high velocity enough to escape the Earth's gravitational force. Rockets are the excellent examples of the application of Newton's third law. Thrust of the high pressure gases by burning fuel from the engines pushes the rocket up with a very high velocity enough to escape the Earth's gravitational force. So try to understand here. Same, a gun recoil while firing. The gun is firing, the bullet is moving. This is the bullet, this is the gun. A gun recoil while firing, it means that the gun is pushing back when the bullet is fired at a high speed. That is the Newton's third law. Rockets are excellent examples of an application of the third law, Newton's third law. The thrust of the so the thrust of the high pressure gases burning. High pressure gases are burning. For example, it is action. Fuel from the engine pushes the rocket up with the high velocity. It is reaction. It is moving up is reaction. Reaction. Enough to escape the Earth's gravitational force. What I am saying? The Newton's third law application gives the rocket. So rockets are an excellent examples of the application of the third law, Newton's third law. The thrust of high pressure gases by burning fuel from the engine pushes the rocket up with a very high velocity, enough to escape the Earth's gravitational force. The burning gases, high pressure gases by burning fuel behaves as action, so it will move up, that is reaction. So burning fuel from the engine pushes the rocket up with a very high velocity, enough to escape the Earth's gravitational force. So trying to this, while walking, we push the ground back. This causes our body to move forward. You see, he is walking. The boy is walking. While walking, we pushes the ground back with our legs. This causes our body to move forward. So try to understand here. While walking, we pushes we push the ground back. This causes our body to move forward. Here, swimming, you can see here swimming, swimming. While swimming, we push the water back like this or like this, making our body move forward due to the Newton's third law. So coming to bird, this bird push down the air with their wings like this. Birds push down the air with their wings, causing them to stay up in the air and move forward. So while the walking, the foots are pressing with action, the push the ground back reaction. This causes our body to move forward. While swimming, we push the water with action, making our body move forward with reaction. So, due to the Newton's third law, birds push down the air with their wings with action, causing them to stay up in the air and move forward is reaction. So, these are the Newton's third law of real world examples. So, coming to next video lecture. So, summary of the lecture, this video lecture. This video lecture provided fundamental or foundational understanding of Newton's three laws of motion. In 1686, Sir Isaac Newton introduced his three laws of motion. He introduced three laws of motion depending on force and motion. These laws are known as Newton's laws of motion. So, in this video, the video lecture provided a fundamental understanding of Newton's three laws of motion, which form a core of classical mechanics. So, first law, which introduces the concept of inertia. The Newton's first law is also known as law of inertia. The measure of mass gives the inertia. So, which introduced the Newton first law, which introduced the concept of inertia and explains how objects resist changes to their state of motion. If less mass object has less inertia, if the mass is more, the inertia is also more. The Newton's second law was examined through its mathematical formula F is equal to ma, showing how force, mass, and acceleration are interrelated. So the rate of change of momentum is directly proportional to net force acting on it. The rate of change of momentum of an object is directly proportional to the net force acting on it is the Newton's second law. Newton's second law. So the Newton's second law was examined through its mathematical formula F is equal to ma, showing how force F, mass m, and acceleration a are interrelated. An essential principle in computing motion in physics engines. The third law, for every action, there is equal and opposite reaction, is the Newton's third law. The Newton's third law, stating that every action has an equal and opposite reaction, was discussed with real life examples and real world applications such as walking, drone flighting, and rocket propulsion. So, in our coming video, we will explain that is understanding of gravity. In this understanding of gravity, we will learn initial state, no understanding of gravity, gravitational force, F is equal to gm1 m2 by distance square. Depending on gravitational force, we need to understand real life examples and computing relevance. We need to discuss effects of gravity, free fall orbital motion, weight, etc. We will discuss final state understanding gravity's rules also. So thank you so much. Thank you for interest on this video. Thank you. Thank you so much.